I start, I should also thank all our funding agencies. You can see all of their names, at least the ones that have funded this particular work. And I should also thank the Canadian and Albertan taxpayers, because it is their money that allows us to study these concepts. So the topic that I've chosen today is CO2 capture for mitigating greenhouse gas emissions. So this is an area that we have been studying, not in a very broad sense, but at a technological sense for the last, I would say, about 10 years. And I believe we have added significant amount of knowledge in this particular area. As I told you, there were two reasons why I accepted this talk. And before that, I will just make sure that I turn off my camera so that I get the bandwidth. So there are two reasons why I accepted. So the first is I wanted to congratulate Professor Anand Raman from NIT Trichy. I've not studied under him, but I have had the pleasure of knowing him for a very, very long time. And I have benefited from his advice, from his mentorship. And also many of his students came to us for doing their postgraduate studies, and they've been wonderful. So originally I was asked to give a talk at his retirement celebration, but I couldn't make it. And I heard that that celebration could not go through. So I treat this as my opportunity to say thank you for all his academic and administrative contributions, and also mentorship to me and to many students. The second reason is really because I grew up all my life in Trichy. So both in Township and Belnagar, which is right across NIT Trichy. My mother still lives
Sir,
there.
sir,
Yep.
சொல்லுங்க. Sir,
So
மீட்டிங்ல
sorry, Siva, I think there's okay, good.
Professor Anantharaman has joined.
Okay, good. Okay. So I will also say that I grew up in Trichy, and the big advantage that I gained was that most of my neighbors were either engineers or professors. When we moved to Belnagar, we had many professors from REC, that it was called REC at that time, that were neighbors. We had people like Mr. Vivekanandan, who was from BHL Trichy. So these were all people who inspired people like me. So it was, Trichy is a very integral part of my life. And I did all my 14 years of schooling at RSK, and um, there were outstanding teachers. Like I remember Dr. Rajagopalan, Lloyd, Jayaraj, Mrs. Rani, and many others. I think these were the real heroes. When I think back at the amount of dedication and commitment that they had to their profession was outstanding. Especially considering the economic situations at which they were living in. I think they were selfless, and and their contribution cannot be valued. So I think that is a very important part of growing up in BHL. My first exposure to greenhouse gases was through my father. My father worked all his life for at BHL, both in Trichy and in Ranipet. So I think this was around late 80s when he said that he had to attend some kind of an interview for a promotion. And he said, yeah, they're going to talk about something like greenhouse gases. So he said, I need to go and read something about this. And that was my first time that I heard something about greenhouse gases, the greenhouse effect, the global warming, and so on. But that was a long time ago, so I never took it seriously. But I never knew also that my life will be spent a lot on studying this aspect. So with that, I'll move into my technical talk. I've split the agenda into two. So in the first half, I'd like to talk about CO2 capture, a very broad overview. I will not go in too deep into that. And then the second half, I'd like to talk about our research in this area. What are our contributions? And we have been working specifically on adsorption processes for CO2 capture. I would introduce what adsorption processes are and what are the challenges and how we are contributing to overcome some of these challenges. Of course, this entire talk will make sense only if we assume that human-induced climate change is real and CO2 plays a key role. I do believe that this is true. But this is a point of contention all around the world. It has the power to change elections. If you don't think that this is true, I would still urge you to look at the talk as a purely scientific talk, because the engineering challenges that we face here are significant. So let's go in. So the first part of the talk is on CO2 capture. So here is the plot of the CO2 concentration in the atmosphere. And I looked up over the weekend. It has steadily increased, and it has reached a value of about 413 ppm. And this is continued to climb, although this year has been, I would say, one of the first years in a long time where CO2 has actually taken a dip because of the COVID pandemic. But still, atmospheric CO2 compositions and concentrations start rising, and this is going at an alarming pace. So the other aspect to consider is also the temperature anomaly, which is a kind of average difference between the temperatures in the 50s, and we see how that temperature anomaly has, on an average, is on the upward trend. Many people consider 1.5 degrees change to be fairly catastrophic in the sense that irreversible climate change could happen under those conditions. And many countries globally have seen this, have accepted this, and are taking measures to control this. So, and this is I would say, in addition to things like the pandemic that we are seeing today, and in addition to many fundamental issues, this is a global issue that has to be addressed, and the challenges are plenty. So if you look at the source of greenhouse gases, I've shown you here two aspects. So one is, what are the different kinds of greenhouse gases? So we often tend to think of CO2 as being the only source, but you can see that of course, that is true, because 76% of the greenhouse gases tend to be CO2, but there are also others. For example, methane that comes from farming has a big contribution. The other reason for methane emissions has also been fugitive emissions from methane production, for example. And there are also others that contribute to greenhouse gases. But also note that some of these gases, for instance, methane, are considered to have 30 times more greenhouse warming potential compared to CO2. So although their percentages could be pretty small, their contribution towards global warming is fairly high. So we have to take those into account when we are looking at these numbers. Not all these gases contribute in the same manner towards climate change. So if you now look at the emissions by sector, and I will show this later. So the big contributors are, of course, electricity, heat production, industry, and this would include heavy hitters like steel, cement, fertilizer. So these are very large in size, and they also consume a lot of energy. So these tend to be fairly large. And I will also show you another way to look at the same idea in one of the following slides. So this gives us a context to look at what the problem is. So this is really, I would say, chemical engineering year one, where we teach mass and energy balances. And Professor Anantharaman has even written a book on process calculations. And this is a very, very simple way to illustrate what happens with the CO2 balance, for example, or the greenhouse gas balance in this case. So if you consider the atmosphere and the ground, you can see that there are several contributions from the ground to the atmosphere, with energy, industry, and transportation being the big hitters. And these are all represented in gigatons of CO2. So 1 gigaton is 1 billion tons, or 10 power 12 kilograms. So what we are talking about is a fairly large amount of emissions that happen because of human activity. So, and as you can see here, this contributes to about 39 gigatons. So for want of a simplicity, you can think of 40 gigatons to be approximately the amount of CO2 that goes from human activities on the ground to the atmosphere. And of this, India contributes about 2.37. So on a global scale, this is a significant number, but in terms of per capita emissions, this tends to be low. And that is also reflected because of our energy needs have been much lower than many other places. Of course, there are also sinks. So which means there are activities that take the CO2 and sequester it on the ground. And this happens in two modes. So one is in ocean and in land. And these two are the biggest contributors, and they contribute to about 21 gigatons of CO2. So what you see immediately is that we are adding 39 into the atmosphere, and nature kind of removes about 21. And this is on an annual scale. So if you use a very simple mass balance expression, which comes from the law of conservation of mass, accumulation is simply nothing but in minus out. Of course, there is generation and consumption. Those numbers tend to be fairly small when we are looking at the big pictures. But what you see is that we are adding a net of about 12 gigatons of CO2 per year into the atmosphere. And as I can show you here, a lot of that comes from energy and industry. Transportation is a fairly challenging option to mitigate because many of it contains moving systems. Whereas if you look at energy and industry, they tend to be thought of point sources. So where you have the opportunity that the energy production is concentrated in one place. So if you want to now remove CO2, then there is a better opportunity for us to do it there as compared to in the transportation industry. So let us look at a conventional system. This is a very oversimplified picture of what happens. So traditionally, and I think most of the audience are no strangers to this, BHEL is one of the most renowned uh, uh, companies, and especially Trichy is the center for boiler making. So a lot of power generation happens through the contributions of many of you who are attending this talk. And what you see here is fossil fuel goes into either a power plant or a chemical plant. And very often uh, as we all know, the fossil fuel contain predominantly carbon and hydrogen. So these are the two big atoms that we are interested in. And the way that I have learned from um, some so from many colleagues who are much more knowledgeable than me is to imagine fossil fuels as containing two atoms, essentially atoms of carbon and atoms of hydrogen. Hydrogen is where you get the energy from, whereas carbon gives you the density. So the higher the percentage of carbon in the hydrocarbon tends to be dense. So that is why if you look at methane, it has four atoms of hydrogen to one atom of carbon. Whereas on the other end, you can think of, for example, oil contains CH2 approximately, give or take. So four becomes two, and coal contains CH. So essentially, for every atom of carbon, you have one atom of hydrogen. So, and that is the reason you see that as you go through this chain, the density changes, and of course, you make the transition from a gas to a solid phase. So, you take the fossil fuel, it is consumed in a power or chemical plant, and the emissions, in this case, I've considered CO2, is put into the atmosphere. So now if you look at this entire chain, we could contribute towards mitigating greenhouse gas emissions at each point in this transition. So, and again, I would say that this is a completely oversimplified version of what really happens. So, pardon me if I missed something or if I've oversimplified anything. So the first thing is we could start from the left. So how can we now reduce the CO2 emissions? And of course, the point being that we continue to have power production and chemical production at the current scale or at increasing scales because population is growing and the demands are also growing. So I think that would be a completely different angle to look at it. So if you look at this, so we could uh, contribute by doing the following. So for example, at the fuel level, we can think of fuel switches. For example, there is a big shift from coal slash oil to methane, natural gas, in other words. Uh, Canada, Australia have huge gluts of natural gas and contributed by the COVID pandemic and for quite some time now, methane prices and natural gas prices have been very low. Several liquefied natural gas facilities have been built. Huge tankers of methane has been built. And with the idea that many countries, for example, Europe just announced a couple of weeks ago that by 2050, they are going to go to a net zero CO2 emissions world. So which means that they want to have no CO2 coming out of the countries probably in the next 30 odd years. So from that perspective, methane seems to be a fairly clean fuel. And you all know that compared to coal, dealing with gases are much, much easier, and it is also clean. Of course, another big area, which I believe where the big changes are going to happen, is also in renewables, solar and wind. Battery technology has become much better. Batteries are much cheaper compared to what they were 10 years ago. The grids are slowly being modified as well. So I believe that is another aspect that will help us to impact this chain at the source level. What else can we do? So if you go down to the power of the chemical plant scale, of course, efficiency improvements are a big role to play. So these are what many people call as the low-hanging fruits. And it is often overlooked because very often it is not a very fancy research topic, but on the other hand, on the ground, this has a huge role to play. And we can also think of alternative ways of power generation. For example, combined cycle plants have a higher efficiency, but also higher costs. So very often you start seeing this interplay of efficiency, CO2 mitigation, and the cost. And very often the decision might not be a straightforward one. Then at the emissions level, what we could do is we can also consider carbon capture, storage, and utilization. Utilization is a word that has become more popular in the last 10 years, and I will talk very briefly about this. Yet another way is once you have emitted the CO2 into the atmosphere, are there any ways in which we could now do something to reduce its impact on the climate, for example? And people have been talking about geoengineering, where you seed the clouds, you play around a little bit with aspects which have traditionally not been touched. And the other big area people have now started looking at is direct air capture. So which means that instead of capturing CO2 from the outlet where it is fairly concentrated, you capture it from the atmosphere. Remember, in the atmosphere, the concentration or the composition is about 400 ppm. Whereas if you look at a coal-based power plant, you have about 15% CO2. So you are talking about a much, much more dilute stream to capture from. But there are many startup companies that have been focusing on this direct air capture. Costs are very expensive, but that is also a way in which we could start looking at what is now being called as negative emissions. So where you reduce the concentration of CO2 by actively removing CO2 from the atmosphere. So I believe that a future society would run mostly on these and possibly with many of these other things. But I think this is where the main contributions would be. Whereas we should probably look at many of these techniques, such as carbon capture, direct air capture, to be bridging technologies that will allow us to move into the future. But why do I say that it might not be 100% possible is that many processes that we operate today cannot simply move from fossil fuels to renewables. For example, chemicals, if you look at polymers, if you look at any chemical or most commodity chemicals, if I may put it that way, trace their source back to a carbon or a hydrogen source. So in those places, it would be very difficult. And in fact, the energy penalties tend to be very high in order for us to move from depending on fossil fuels to moving to a completely renewable source. So which means that many scenarios that people are looking at consider fossil fuels being increasingly used only for producing chemicals, whereas we look for other sources for producing energy or power. So which means that provided that we have these carbon sources, and if we want to stop these carbon molecules from ending up in the atmosphere, even in those kind of scenarios, the carbon capture and storage becomes an important tool. So this is the topic that I would be talking to you about today. Okay, so what is the concept of carbon capture and utilization? Let me just show this to you in a very simple schematic. I should thank Professors Karimi and Farouk from NUS who helped me developing this framework. So the traditional framework is the following. So you have a power or a chemical plant. We take fossil fuels or any carbon-based fuels. And the main idea is to either produce, I would say, electricity or energy and or chemicals in this, if it's a chemical plant, of course. And what we produce in addition to producing power is a CO2 stream, which is typically called as a flue gas. Depending on what you're burning here, you can end up from anywhere between 5 to 40%. For example, if you look at natural gas, if you burn natural gas, your CO2 concentration typically is in the range of 4 to 12%. Coal gives you about anywhere between, 4 to 8% in terms of natural gas. Coal gives you anywhere between 12 to 15%, and so on. Um, so you have a fairly dilute stream, and this is where the big challenge arises. And the idea is that we are going to build a capture plant where the idea is to concentrate the CO2 that comes in from here and to enrich it. And typically you want to enrich it beyond at least 95%, because any contaminant here, one, could affect your downstream operations, and or you're also going to spend a lot of energy if you want to store the CO2 under the ground. You have to pressurize this up to about 120 bar pressure, and you might be ending spending a lot more energy on compressing everything but CO2. So there is a huge necessity to concentrate this from about 5 to 95%. So imagine if you're dealing with direct air capture, you're looking at concentrating it from about 400 parts per million to excess of 95% in purity. Okay, so of course, if you learn chemical thermodynamics, the first thing that you learn is about the concept of entropy. And you will immediately learn that when you have to mix two substances, provided phase equilibrium allows them to mix, mixing is almost an instantaneous process. Whereas if you need to separate any two substances, you need to put in a bare minimum energy. So which means we cannot do the separation or concentration without having to spend energy. And I would say any chemical engineering student who has gone through a course in thermodynamics should be able to do a back of the envelope calculation to understand what is the energy, the minimum thermodynamic energy that is required for performing any generic separation. So what we see in practice is if you look at how traditional chemical engineering processes like distillation have evolved, they typically tend to be around twice or 2.5 to 3 times the minimum thermodynamic energy. So that has been what is practically achievable. So thermodynamics would say that you can go all the way up to the minimum, but practical constraints which show up in the form of efficiencies do not allow us to go there, but that is where most things are. But the important point to note is that when you have to concentrate or separate any mixture, you have to spend energy. And in many of these cases, the idea is that we will take part of the power that is generated in the plant, or you buy it from the grid, as is shown here, in order to perform the capture. So once the CO2 is enriched, we can either store it. And of course, this requires energy because you need to compress the CO2 to very high pressures. So you require energy. And or you could also utilize this CO2. So what do I mean by utilization? The CO2 can be taken in and you can be processed further. And this will, of course, require, and this is very often forgotten, that you will require additional raw materials such as ores, for example, or hydrogen. When people are talking about methanol synthesis, hydrogen has to come from some source. And very often we have to be careful that these are not causing adverse effects on the environment. So once we do this, again, this would require energy because CO2 is a fairly stable molecule. So in order to convert the CO2 into something else, you would have to put in energy. So the question is really how much extra energy would we need? Are we doing more harm by trying to capture CO2 or by putting in more energy? So in this case, and what is important to note is that this energy should preferably be renewable. And then you make products. So what you see here is also that the products that we produce here have to have long-term sequestration potential. For example, a common assumption is, yes, we can now put this into soft drinks, or we can even convert it to urea. But if you look at the life cycle of these approaches, the CO2 molecule eventually ends up going back to the atmosphere within a very short period of time. So we need to think of a very long-term sequestration potentials. The other point to note is that parasitic energy, the ones shown here in red, is rather unavoidable, and we need to find better sources of this energy. So here is the carbon capture storage schematic that was published by the IPCC, the Intergovernmental Panel on Climate Change, a long time ago. And I would say this is a fairly reasonable representation, although I think the specific components have evolved over time. So the idea is that we will start with many raw materials such as coal, biomass, oil, and gas. So they all come into industries, electricity, cement, and other industries. And the CO2 that is being produced here can be stored, for example, in different ways. And for example, ocean storage is one where we try to store the CO2 in saline aquifers under the ground. Geological storage is where most activity has happened. So these are depleted oil wells. It's a place where there is space available, and and there are also formations which has to be monitored, which has to be characterized. And the idea is to pump CO2 under the ground and cap it and monitor it, and then see and make sure that it does not come out. This has been a fairly, I would say, a controversial subject as well, because people are naturally worried that there would be cracks that happen in the ground and CO2 might come up. But on the other hand, there are also several projects that have successfully managed to do this. Of course, the other option is to use it for what is called as enhanced oil recovery, where you try to pump CO2 to remove oil that was otherwise difficult to remove. And in these mass balances, you see very often that there is still a net CO2 storage potential as compared to the amount of oil that you will take out. So very often it is these aspects that have, I would say, have taken shape. The other aspect where I think also in India there's been scope as discussed by research papers is also in coal mines or in coal seams, which have very poor, I would say, thermal capacity, but you can now absorb CO2 on these coal seams in order to store it for a very long period of time. So when you look at cost becomes a real driver in terms of CO2 capture. I'm trying to give you a broad perspective of how the capture scenarios are. And I would say still the numbers, although we are getting better clarity about these numbers, but if you read the literature, it's everywhere, and you have to be very careful in interpreting or to making your bets based on that. Capture typically takes about 15 to 75 US dollars, and these are all reported in US dollars per ton CO2 captured. The transportation, it's worth noting that, for example, right here in Alberta, where I'm talking from, there is the Alberta Carbon Trunk Line, which is about a 200-kilometer long pipeline that's moving CO2 from one place to the other within the province, from the source to a sequestration site. So those kind of CO2 pipelines are being envisaged both in North America specifically and also in Europe. So the transportation takes anywhere between $1 to $8 per ton. And finally, the storage is anywhere between $1, I would say, to about $30. So if you look at this entire chain, you immediately realize that the capture is where most of the expenses are. But it's also important to point out that there is technology that is available for each of these steps, but cost is generally the one that is prohibited. So if you look at carbon capture, especially in power generation, we could look at it in these ways. There are different ways in which power is generated. The most common, I would say, the biggest contributor to power is what is called as post-combustion. These are typically the kind of combustion cycles that we see I would say in most places, because this is the cheapest, and this has been historically the most advanced in terms of history of advancement. So the idea here is that we burn fossil fuel in the presence of air. So this contains about 20% oxygen and about 80% nitrogen, give or take. And what you produce in the combustion is CO2 and nitrogen. And of course, you produce power. And the idea is now to concentrate CO2 here. So you put a CO2 capture unit, and then you compress the CO2 and send it out for storage. So this is called post-combustion. Um, this is important because, as you can see here, the CO2 capture unit is built downstream of an existing combustion unit or an existing power plant. So what this means is that this can be retrofitted to any available power plant. And there is a lot less interaction with with the power plant itself. So in terms of reliability, it tends to be fairly high. But on the other hand, the biggest challenge, as I will talk to you later, is the the conditions at which you get your flue gas. The second one is what is called as pre-combustion, and BHL had a big gasification and combined unit as well. So what you do here is you take the fossil fuel, it can also be biomass, for example, and you gasify it in the presence of air, oxygen, and steam. And what this produces is something called as shifted syngas. So there are a couple of other steps before, but this is predominantly a mixture of CO2 and hydrogen, but this comes out at very high pressures, about 40 to 50 bar pressure. So the concentration of CO2 in this stream compared to that in the post-combustion is fairly high. So as a chemical engineer, you know that when your concentration and pressure is high, the volumes that you treat tend to be much smaller. So it is, although we'll pay in terms of pressure vessels, the volumes tend to be much smaller. So the idea here is you do a CO2 hydrogen separation, where the CO2 is sequestered and the hydrogen goes into combustion. I've simplified a combined cycle plant as combustion, and you produce power. Of course, there is the technology available. There is technology available for NGCC, natural gas combined cycles, also for coal that is available. There is biomass is available, co-firing is available, but this tends to be expensive, but on the other hand, also highly efficient. So for every molecule of fossil fuel that we put in, you tend to produce more power in terms of pre-combustion as compared to post-combustion. The third one is oxy-fuel, where you take air and you separate air. So which means you've removed all the nitrogen from here and only the oxygen goes into the combustion, into the boiler, and you burn that in the fossil fuel. So what you get here is a fairly high purity CO2. Of course, we know that this would mean the temperatures here would be very high. There are also other operational issues, as I understand. So there is a possibility of recycling CO2 to remove that. For some reason, oxy-fuel has not taken up very much in the industry. So what I'll do is I'll focus on post-combustion for the rest of my talk. So this is a typical plant. I don't have to explain this. I'm sure everyone in the audience today is involved in this in one way or the other. So this is a typical coal-based power plant. I'm looking at a classical 500 to 550 megawatt power plant. So you burn coal in the presence of air. It produces close to 55 to 60,000 tons of flue gas per day. A good number to think about is for 500 megawatts, we produce close to 10,000 tons of CO2 per day. And the challenge is that this is coming out at atmospheric pressures and at or around room temperatures, depending on what are the emission standards and how much heat has to be recovered and so on. But this is a good idea. You will see variabilities in this, but this is a good picture. So we need to now perform the CO2 capture. We need high purities. And we also, if you look at some of the requirements, for example, the US Department of Energy is considered a big player in this. They set regulations, and they also require that 90% of the CO2 that comes into the plant ends up in the product. So this is what we call as recovery or yield in many cases. And as a chemical engineer, you immediately realize that as I start expecting to remove more and more, the challenges become increasing. So, and of course, this has to be done by removing as less power as possible and with as less capital expense as possible. So if you look at the worldwide CCS project, so this is the map that is provided by the Scottish Carbon Capture and Storage organization in the UK, and they show a map of different CO2 CCS projects in this case. As you can see here, most of them tend to be concentrated here in North America, in Europe, and in parts of China and Japan. Australia also has a big program in CO2 removal. And as you can see, there are also two projects in southern India. One is in Thoothukudi, in Tuticorin Alkaline, in TAC, which is operational. And the other one is slated to be at Dalmebron, in the cement factory there. So these are, this is a snapshot of different CO2 projects. There are major injection sites, I would say, here in Africa, in in Norway, and here in Canada and in the US. And I'll show you an example. The two projects that I would like to highlight, not just because they are from Canada, but these tend to be the biggest in scale. The one is the Boundary Dam project in our neighboring province, which is Saskatchewan. So this is the first large-scale post-combustion demonstration unit. It was built at around $1.5 billion Canadian dollars. So it's a huge installation. As you can see here in this picture, so this is the power plant, and you can see that there are about 4 stacks. So there, I think they have 5 units, 510 watt units. And here is where the CO2 capture unit is. And this is for just one of these units, which is for catered for 110 megawatt plant. The CO2 that is captured here is sent to, is sold to another company, and they use it for enhanced oil recovery, and the CO2 gets stored. And as I'll show you, this is using a process called as amine-based capture. So they are designed to now capture and sequester 1 million tons per year. It was, in fact, in the last few months or the last year when this plant has been almost running at 95% capacity. So it is now fully mature and it is fully running in a consistent manner. It had a lot of startup issues which they have overcome, and also the scale of this is much bigger than the typical chemical processes that we have seen. The other one is in Shell Quest. It's called, the project is called Shell Quest. It's just about 60 kilometers north of where I'm talking from. And this is CO2 removal from hydrogen. This is an hydrogen upgrader. Hydrogen is required in an upgrader to treat the Alberta oil sands. And this is again scheduled for or designed for 1 million tons per year. So just a couple of weeks ago, they announced that they have successfully stored 5 million tons of CO2. It's not a huge number when you think about the 40 gigatons that we spoke about, but these projects show that there is long-term viability in doing this. So here, there is no oil recovery. CO2 is just injected under the ground. So this is the process at Saskatchewan, the Boundary Dam. And this is a classical process. This is a process that is taught in undergraduate classes and heavily used in the industry. I used to be a trainee at SPIC in Tuticorin, and one of the areas that I had to supervise or to assist in supervision, I think that's the right thing because I was still a trainee, is in the what is called as the CO2 backend. So, and as you can see here, the idea is that you have a boiler which produces power. The flue gas comes out. You remove the SOx and the NOx here, and then it enters the CO2 removal area where you have a CO2 absorber. So you have a liquid that is flowing through this system. It is an amine-based solvent, and it reacts with the CO2. So what leaves this stack here is almost a nitrogen. So the CO2 that is now captured in the solvent is heated up in what is called as a regenerator or a CO2 stripper. And the concentrated CO2 is taken here, and then it is put back here. So if you look at this entire schematic, the big challenge is here. The steam and the energy that is required for regeneration is, I would say, exorbitant. That is where most of the energy consumption in this process goes to. So now we have this technology. So then what is the challenge, right? So this is a mature technology, but the amines are very prone to degradation. And this is a very acidic environment. So the walls of these huge towers tend to corrode. And some of the byproducts of the degradation of the amines are also known to be toxic, so that there's a big concern of moving away from some of these technologies. And there is, of course, a high cost, which is anywhere between $40 to $60 per ton of CO2 capture. So all of this are the drivers for people to start looking at alternative technologies. So what is it that we do in our lab? And this brings me to part 2 of my talk. So I've given you an idea of what is a CO2 capture, why is it important, and what are the technologies that are available, and what are the challenges with those technologies. So the next part, I'm going to talk about what are we doing in our labs, so that you also get a glimpse of the kind of activities that we do. So we use a different process, which is called as an adsorption. This is not new. I think most of us have an adsorbent at home in one way or the other. This is with a D. So in these adsorption processes, we use what are called as porous materials, sometimes called as molecular sieves. So these tend to be carbons, zeolites, metal organic frameworks. And when you zoom in to these solids, these tend to be microporous. So they have pores in the order of nanometers. So very, very tiny pores. And they also tend to have surface areas, and the surface areas keep increasing over the years because people are finding out newer materials. So earlier it used to be about 500 square meters per gram. Now people are reporting materials that have a surface area of about 10,000 square meters per gram. So for those of you who are in and around BHEL, 10,000 square meters is about half of the Nehru Stadium right next to RSK School. So if you take one material, 1 gram of material, that is how much space that is available, provided you're a gas, right? So this is used in ion exchange, water purifications, odor, color removal. And what has happened in the last 10 to 20 years is that we have, when I say we, our colleagues in chemistry have had better ways of making really excellent materials that can be used for separation. So what it means is that when you now have one of these materials, if you now let it phase CO2 and nitrogen, what I've plotted here is called as an isotherm. So as a function of pressure, I say for at a given pressure, how much of CO2 can be sitting on the solid, and that is called as Q star. So most materials tend to take CO2 as compared to nitrogen, because I'm talking about these two components because these are the predominant components in the flue gas that we spoke, right? So what we do is we take some of these materials, and if you put it in a column like this, and if you send it a mixture of, let's say, CO2 and nitrogen, and I'm going to show you how this will transmit through the column. Let me see if I can get this started. So as you can see here, originally the column has none of A and B. And when you now start introducing, you see that since B has a lower affinity to the solid, it propagates earlier. So which means if you start measuring what comes out of the column here, you start seeing a pure nitrogen breaking through the column. And if you wait there for long enough, for a period of time, you will get nitrogen in pure quantities, and slowly the CO2 will start coming out. So what you have here is an opportunity to collect the nitrogen in the pure form. And this is in fact the exact technology that is used in medical oxygen concentrators, which have come back into the light, especially after the pandemic. So in this case, you use a zeolite, which absorbs nitrogen, but does not absorb oxygen to a great extent. So that can be used to make oxygen concentrators that typically concentrate oxygen up to about 93 to 95% oxygen. And it's also used in huge hydrogen plants where hydrogen is purified. So the point that I want to make is that the technology is available to go from anywhere between 3 normal meter cube per hour to about 400,000 meter cubes per hour. So this is a huge range, but still not huge enough for a process like CO2 capture that we have been talking about. So in these processes, the process alternates between two steps, the adsorption and the desorption steps, because what happens here is when you let the entire column now saturated, you see that beyond a certain point, you cannot use the solid anymore because the solid is completely saturated. So at that point, you have to clean. This is exactly what they would call in the boiler industry as, for example, if you're looking at an ion exchange resin, this is what is called as a backflush. So when you do a backflush, you're desorbing everything. But when you're dealing with a gas, you have two main ways in which you can do this. One is you can reduce the pressure, or you can increase the temperature. So this is called pressure swing adsorption when you decrease the pressure. When you increase the temperature, this is called temperature swing adsorption. And these are both available options. So our group has worked a lot on using PSA for a CO2 capture. Okay, I will. Before we go through this, I will highlight that if you now put in a feed, you get two products. One is called as a raffinate product, and the other one is called as an extract product. If you compare adsorption processes to those that are taught in undergraduate level, the separation processes such as distillation and absorption, the key difference is that this is an unsteady state operation. So there are no explicit steady state design principles that are available to design these processes. So this is a huge issue when it comes to designing these processes. And that also explains why they are often not taught at an undergraduate level in a more rigorous manner. Because in terms of chemical engineering design at an undergraduate level across the world, we almost teach steady state design, whereas these processes inherently operate under non-steady state. Um, so I wanted to show you this slide. These are the typical equations that we solve. This is uh, neither meant to brag nor meant to scare the audience, but just to make a point that the calculations that we show later on are not simple. For example, young people that might be watching this should not get the idea that this is straightforward, but by a good training in math and by good training in computer programming, they can, in fact, solve many of these problems, provided they put the time and effort into this. So these are the equations. These have to be solved. So we do have a fairly good computers these days, but the scale of doing this, for want of simplicity, is pretty large. So as you can see here, I can now take one column and I can combine this in many different ways to come up with a process. So I can pressurize the feed. I can have a feed step where there is gas going in and gas coming out. I can close one end and pull vacuum on the other end so that I'm desorbing this column. I can take the gas from one column and put it in another. This is called as pressure equalization. And this is a classic reflux step where you take some of the gas from here and use it to clean the other bed. So what you see here is that these tend to be like now like building blocks. So you can now start combining these steps in order to make a process. For example, I show you a process here, very simple process. But the point that I want to underline here is that you have several variables that you can play around with. You can change the velocity at which you want to put it this in. You can change the adsorption time. You can change the pressure levels at which you want to now operate this entire system. So in summary, for a very, very simple process like this, you already end up with about 8 operating parameters. So the question of how do I pick this 8 operating parameters so that I maximize the potential of the system becomes a fairly challenging problem. I will skip this. And this is accelerated by the point that, as I told you, these processes have fronts, as I can see here on the left-hand column. I show the fronts that are moving back and forth because this is a cyclic operation. And on the right, I show you what happens at the process level. As you can see here, if I now move all the way here, after doing this for about 50 times, you see that the purity of the CO2 has gone all the way up to about 80%. You also see the temperatures in the column keep changing as a function of time. And this is exactly where it becomes difficult. If I give a certain set of input variables, it becomes very difficult to predict what what the process will give us. So for this, what we do is, I'll skip this for the want of time. But what we do is now, how do I now pick these parameters? What we do here is a technique called as optimization. So we have a full model. This is essentially the set of equations that I showed you before. And we have what is called as an optimizer. What the optimizer does here, it takes a random combination of all of these and sends it to the model. And the model evaluates how the process will perform. And then it'll throw it back as performance indicators. These performance indicators could be energy consumption of this process, for example, or the purity of the CO2 that I achieve for a given set. And then you can now say, okay, if my purity does not reach a certain value, I don't want that to happen. So if you do this over thousands of unique combinations, we get what is called as an optimal front. And in this case, for example, I'll show you. So each of these points is a unique operating condition. I'm plotting purity and recovery. In any process, I want to get a high purity and high recovery. So I want to be as close as possible to the top right corner. So as you can see here, when the optimizer keeps doing this over and over again for thousands of of operating points, you see slowly that we end up with what is called as a trade-off plot, which is called as a Pareto curve. So this is named after an Italian scientist, Pareto. And what you see here is that this surface or this boundary separates this entire region as an infeasible region, which means with this process and with the material that I have chosen, I cannot reach any point here. So I have to be contented working in this region. And if I want the best performance of the system, I want to be working exactly on this curve, right? So what this has done is that it has stopped you from doing thousands of experiments and spending time and capital on both human time and on machine time and on consumables. And it has already given you a region where you should be looking to operate this system. Okay. So now, as I showed you, now you can now start building very, very complex processes. And if you ask me which of these processes is going to be the best, it's very difficult, even for experts to say which one is the best. And as you can see here, each of these colors represents each of these processes. And as you can see here, the same material operating within the same operating range, but just changing the configuration can give you, I'm sorry, the axis does not show. The x-axis is purity, y-axis is recovery. As you can see here, it can completely change the outcome of the process. So what we have developed, and when I say we, it is the scientific community, uh, the whole goal is to go from material properties and using a model-based optimization in order to predict what happens in the large scale. And of course, the big question that would be in your mind is, does it work? And the answer is yes. For example, this is a project that we did with a company here. They make oxygen concentrators for aquaculture. We made measurements based on 350 milligrams of material, and they ran experiments up to about 750 kilograms of materials. And you can see that we can predict with no other extra fitting parameters. Purity from this 750 kilogram machine can be predicted to about 1%. The recovery, we were off by about a few percentages, and the energies are very close. So the point being that if you, let me see, why is this? Yeah, this is a 2 million times the scale up. And why do we have to do this is to make sure that we are looking at the right ranges and the models are reliable. Okay. Maybe what I'll do is I'll skip this for the time being, and I'll gladly answer this at a different time. But what I wanted to emphasize this is here. What we can do, we are at a position where based on crystal structures, which chemists measure on very, very, very small quantities, it is now possible through the use of computers to predict the thermodynamic properties and feed them to computer-based process optimization so that we can now screen, let's say, over thousands and thousands of these new materials and ask which of these materials is going to make sense and which has to be scaled up. And as you can see here, we did this by screening a database that contains about 5,000 specialty materials called as MOFs. And we were able to identify a whole bunch of adsorbents that can do better than the state-of-the-art liquidity scrubber. This was a huge effort. This represented for us about 5 million unique combinations. It took us a couple of years of computational time to do this. But the idea being that you could now use these approaches for making decisions about which material to choose. So I'll summarize. When I summarize, I have to be very clear that uh, the best design is to avoid the creation of any waste. So if you can avoid CO2, that is the best way to do things. But if it is unavoidable, then we have to think of approaches like the ones that I have mentioned. And there are sectors in power, sorry, this skip, chemical and cement that cannot be replaced by renewables. And CCS is a technology that allows us to reach net zero emissions. And finally, CCS is an expensive area, but that is why there are a lot of research projects that are going on. And it has to happen both in the academia and in the industry. Ultimately, I would say the price of carbon will decide whether this will work or not. And this entire thing makes sense only if carbon has a price. Okay. But this is also to let you know that if you have young people that are interested, the clean energy is a big challenge. It's a global challenge. And if they would like to be challenged in these kind of areas, I would urge them to start pursuing studies in this area. Okay, so with that, I conclude, and I'm happy to take questions. Hello, Siva.
Hello. Thank you, Arvind.
Yep. Thank you.
So we'll have a formal say by chairman, and subsequently we'll have a vote of thanks.
Any clarification from sir? Please proceed, sir.
Dr. Nagasamy has a question.
Sir, unmute your things and please proceed.
Sorry. It's a good presentation, a good analytical work coupled with the mathematical equation. Your CCS system, which absorbs carbon, whether my simple question is whether it can be adapted for automatic, so that I had somewhere some 5 years or back something like catalyster attached to the silencer of an automobile, by which you absorb the CO2. I heard somewhere, but I don't know any work is on that or not. The catalyst, like I think it is something like zeolite based, similar thing only, nanoparticle added, something like that only. They added the system by which your emission level has been reduced. That's one point. The first point is, you said that your ocean is storage. I also read somewhere in IPCC that report that sea sand, that is the seashore sand is the best absorber of CO2. And they have done some experiments and with the sea sand and pumping the CO2, and they were trying to convert such sort of energy to get some energy from this sea sand, because sand, the silica absorbs the CO2 and it becomes something else, and from that you try to get some energy. So that is I don't know how any work has done on that.
Okay, so I'll answer the two questions. Very, very interesting questions. So the first one is with putting essentially a CCS unit on the back of your car, for example. There are a couple of issues with that. One is if you compare it with the SOx and NOx emissions, the amount of CO2 that an automobile produces is huge. So what we are doing is we are taking the carbon molecule that comes from petrol, and we are taking 2 molecules of oxygen from the atmosphere, and we are converting it to CO2. So in fact, you're increasing the weight of your product. So what you're doing is you're increasing the payload of your car as you keep traveling, because the car becomes heavier and heavier, because you're taking all the CO2, you're taking the oxygen from the air, and you're storing it in your car. The second aspect, the challenge that comes in there is, if I now capture that CO2, what do I do with it? So that from a logistical perspective, that becomes a nightmare. So most of these CO2 capture technologies make sense only at point sources where you have a highly concentrated stream of CO2 at high volumes. And that is in fact one of the big challenges in CCS is very often the places where these CO2 sources are available are not close to the places where you can bury the CO2. So that becomes a big challenge. And that challenge is also reflected in the case of automobiles. So the second aspect is with the sand. It is a process. For example, I did not go into the details. Mineralization is a very well-known technique. It's essentially taking a silicate and converting it to a carbonate. But that again requires a lot of energy. And as long as that energy can be obtained from a fossil fuel-free basis, that is one option. But however, on the other hand, there is a huge pressure on many of the mining companies. So mining tailings are another place where people have been trying to sequester CO2. And there are a couple of example pilot plants that are going on both. Personally, I know some in Australia, some here, also in Canada. So it is possible, but of course we have to be very cognizant of the amount of energy that has to go into such processes. That's huge because they require very often very high temperatures, and that makes the whole energetics a bit more challenging.
One allied question that is slightly carbon monoxide and
Good evening.
NO2, whether any capturing mechanism of carbon monoxide, the capturing will be very difficult.
No, but very often you will never emit CO because there are very stringent regulations because CO is deadly, whereas CO2 is only, for want of a better word, I'm saying CO2 does not kill people immediately. It causes issues at a long-term basis. So there are far more ways in which carbon monoxide is never released, right? So you never worry about that. And the NOx emissions have a much more immediate environmental concern in terms of acid rain and so on. So there are far more regulations on these two gases compared to CO2.
Any effort on IPCC further work is going on for further to reduce to the level CO2 level to the much lower level to the level of ppm or ppb level?
I think that will be huge if you just consider the size of the problem that we are dealing with. And also it is a cost. For example, I showed that concentrating CO2 from a coal plant costs about anywhere between $30–40 per ton. Capturing from the air costs anywhere close to about $600 to $700 per ton. Although some companies have claimed that they can do it at around $150 to $200. But you still see that there is this 3 to 4 times increase in terms of just the cost. And the cost here comes both from the energy usage and from the capital expenses that are required, simply because you're dealing with a huge volume. So if I were to explain this, you now have to process 1 million molecules of air, and you have to sit there and pick these 400 parts. So that becomes also a problem of just size. You have to treat all of this, so your equipment tends to be huge as well.
Yes, it is. I'm from Department of Space, ISRO.
Yep.
So, in the problem is related to the Martian surface or lunar surface, where the CO2 is much larger level. We want to separate out hydrogen and oxygen and make it as a fuel for the re-entry or escape mechanism. There, the separation of oxygen and hydrogen from the CO2, especially in Martian surface, I was told only methane is higher. Methane is higher, CH4. When the methane is more, why not you use methane itself as a fuel and try to escape out? Whether that type of thinking also is being done by SpaceX and Rocketdyne and other thing.
Yes, yeah, no, I'm aware of that, yeah.
So in that connection only I asked this particular question. But anyhow, as you said, my earlier question, I forgot to mention that with respect to the cost effectiveness, that's a thing I was about to ask. You answered for that. Very good.
Yeah.
So I hope further research in multiple area of the universities and academia, you are trying to bring the cost to a very narrow level. That's the work that is going on, I think.
So the simple way to think about this is at some point there has to be a price on CO2, either in the form of tax or in the form of an emission charge, right? So your CO2 capture system makes sense only if the cost of doing this capture and storing is lower than that value. If not, there is no incentive for anyone to do this. So so cost becomes a key driver here.
Last 2 years, California fire, in which there was scientists are thinking whether can we capture CO2 and try to use it in addition to the saving the life and forestry. That was a thinking going on.
Yes, sir.
Thank you. Very good presentation. Thank you.
Sorry for the disturbance. I think that Dr. Arvind has another meeting. So let us reserve the question.
I can still take 1 or 2 questions.
Yeah, one more questions.
Sir, good evening. Hello.
Yeah, please proceed.
Sir, we are able to hear you.
Sir, actually, what I just want to know the stability of MOF. Number one. Number two, the large scale production of MOF. Both are even questioned now. Can you please briefly comment on that? Thank you.
Yeah, sure. Yeah, go ahead. Yeah, you have another question?
Yes, sir. Thank you. That's all.
Okay, he's talking about a new class of these materials called as metal organic frameworks. These are the ones that have revolutionized, or at least there is a promise of revolutionizing separations. So one is, MOFs have traditionally been known as unstable materials, especially in the presence of water. And I think there are several examples that have gone beyond that. We, for example, work with a colleague here in University of Calgary, Professor Shimizu. So they have made materials which are now being commercialized in CO2 capture applications by a company called Savante, also a Canadian company. They are being manufactured in large scales, and they say that the materials are stable. There is a lot, but the cost of the MOF becomes the challenging aspect. So they need to make sure that you're looking at MOFs that are made out of earth abundant materials as compared to scarce materials. Because when you're thinking about the volumes that you require, you're looking at thousands of meter cubes of materials in this case. So yes, stable MOFs are available. They are slowly being translated from small batches to kilogram to ton scale production.
Thank you, sir. Thank you very much.
Thank you.
Shiba, you can
Dr. Shiba has a question. Yeah.
Sir, good evening. This is Dr. Shiba from NIT.
Yeah, hello, madam.
Sir, I have heard that there are many adsorbents in practice, such as your zeolites, MOF, metal organic frameworks, and layered double hydroxides adsorbents. What do you think is the most effective catalyst for adsorption? And one more associated question is AME the only good solvent for CO2 dissolving, or you have any mention about any other solvents which can be used other than the amines?
Okay, very, very good question. So the first question that you asked, what is the best material? The real answer is we don't know. And the reason I say, and please don't get me wrong, it's very often in research, what happens is the more you learn, the less you know. So the more you start looking at what is important, the question, although it seems like it's a very genuine question, but what we see is what people traditionally consider to be best materials do not turn out to be. One, because of the properties that people were looking at were completely off. And the second one is what might look very good on paper, the moment you start putting it into a real world is completely different. For example, even trace amounts of SOx and NOx can kill the material. So in general, what we know for vacuum swing process is that the material has to have a reasonable selectivity between CO2 and nitrogen. And the nitrogen adsorption should be very low. It has to be stable in the presence of water, in the presence of other components. So that is the answer to your first question. The second question, there is a huge amount of work that is being going on in solvents. Amines have traditionally come out to be the best for post-combustion. Otherwise, you can also have methanol, that's physical absorption. So that is also something that people have studied. People have been looking at ionic liquids, but many of them have not moved up the technology ladder. Amines seem to be one of the most commercialized in terms of application, and there are different forms of the amines. And the challenge in using it in a flue gas application is there is a lot of oxygen in the flue gas, and that tends to oxidize your amines. So you have to find the balance between all of these.
Thank you, sir.
Thank you, madam. Yeah,
Thank you.
Kumaresh, I think this is a good time. Yeah.
Yeah, thank you all. Now, may I request Dr. Anantharaman to say a few words? Sir, be brief and
Precise. Be precise. Thank you. So at the outset, I should thank both the IEI Local Center and Tamil Nadu State for inviting me to say a few words about my good friend. I would like to call him as my friend. Though he called me as his mentor, I would like to call him as more as my friend. It was always a pleasure to interact with Professor Rajendran. And in fact, I know him for the past 3 decades. Some of his classmates were my students at REC also instantly. And our relationship grew ever since we started meeting each other. I'm also really surprised that Arvind could recollect my role in motivating him. Of course, we had few good discussions also on various topics in chemical engineering. But it was always, I could see him very, very positive in his frame of mind. Whatever I used to discuss, he always gave a lot of inputs in our discussion. That's where I found him to be a very interesting person. And today he took an interesting topic. Everybody talks about carbon capture technologies, and that's an apt topic today because today our requirement for energy is going up, and our dependence on renewables is not cannot meet our requirement. So our dependence on the fossil fuel, that is conventional technology, is really high. So all of us know that any plant which depends on fossil fuels going to always pollute the atmosphere at great extent. And people are really talking about carbon capture technology so that we minimize the level of carbon dioxide in our atmosphere. Global warming and other things can be brought up. So this is an interesting topic. In fact, I also had the privilege of recommending 3 of our students to work in his lab, and all of them have fabulous experience of working in his lab. To begin with, I should mention about Dr. Ashwin, who finished his MS and then moved over to ETH. Then Vishal is another student who went, and currently I think Bhupesh is also working with him in his lab. So he has been providing excellent facilities, and the beauty is their research is more oriented towards the industry, and that is something which is going to be a very positive thing when they come out of this PhD or MS program, and that's going to really be very beneficial to them. And another thing, the course of his lecture, he also mentioned about this tax. That's a very important thing. Unless you put some value for the work which you are doing, nobody will resort to these techniques. Always people think any work which is towards the conservation of environment, immediately people say it's not going to pay any return to me. Now, if you start taxing them, automatically that tax is going to be a saving for them. And that's where I think we need to bring in some stringent regulations, which will go in a big way. And it's going to really conserve our environment. And another big challenge is we have to evolve a technology where carbon dioxide can be captured at elevated temperature also. And that's where Professor Arvind is working, and he has got huge collaboration with industries. And I think the information which he shared with us should really motivate us to work in those areas and have a good tie-up with industries and try to solve their problems. These few words, once again, I thank Professor Arvind for agreeing to spend some time with us and sharing his experiences and knowledge with us. Thank you so much, Arvind.
Thank you, sir.
Thank you, sir. Next week we have a lecture, Leadership Styles and Impact on Organizational Culture. Dr. Kripa, Professor and former AGM, DHL Tiruchirappalli, agreed to deliver the lecture in association with Computer Society of India and Tiruchirappalli Center. Now may I request Engineer Samidas to propose the vote of thanks.
Before that,
Thank you, Ramdas. Thank you, Goresan. Thank you, Arvind. I'm leaving you. Thank you.
Dr. Arvind,
Yes, sir.
am I audible?
Yeah, audible.
Yes,
Dr. Arvind, you told that your father was an employee of BHEL.
Yes.
If I am right, was he working in Valve's department before moving to Ranipet?
Yes, yeah. He
Then
knows you very well.
I'm happy to note that you are a son of my colleague.
Yes.
I was his colleague when he left for Ranipet, and I'm glad that you had delivered a very beautiful lecture on the CO2 capture. For your information, you know, the thermal plant manufacturing has gone to another stage, that is ultra supercritical boiler, where the emission levels are going to be very, very stringent. And BHL is doing another work on advanced ultra supercritical boiler, which is going to be a sort of a, it will reduce the emission to a very, very higher level. And with that, I think some sort of a solution will come. Anyway, the first statement is best designed to avoid waste or emission is the wonderful statement. Anyway, thank you for your wonderful lecture, and happy to note that Son of the Soil has gone to Canada doing a very important research work, and wish you all the best. Thank you. Thank you all the participants for the patient hearing of this evening. Thank you, Dr. Ramdas, Mr. Ramdas and Dr. Kumaresan. Thank you.
Thank you very much, sir. Thank you.
Thank you.
Thank you. Thank you. Take care. So, thank you, sir. Ramdas,
Thank you,
sir.
sir.